So I want to talk about heats of formation and this particular problem on the worksheet that we did in class today that many of you struggle with. But before we get to that, I want to go back a step or two. And I want to talk about basically the difference between this and this. So the heat of reaction versus Q sub W. Now when we've been seeing these both at the same time when we do calorimetry problems. So when you do calorimetry, you see both of these. So calorimetry is measuring heat, and that calorimetry is really kind of at the foundation of this unit on thermochemistry, because this is how we measure this thing called heat and this thing called enthalpy change. But it's critical that you are able to distinguish between these two, because what I mean is that Q sub W, so the heat for the water, for example, and we're talking here about, a coffee cup calorimeter, and so typically we've got some water in this thing, and then maybe its temperature is going up or it's going down, and the heat absorbed by the water or released by the water is equal to mc delta T. All right. Now, maybe we should deconstruct this as well. So if Q equals mc delta T, let's just make sure that we realize that this T is the final temperature minus the initial temperature. That C is 4.18 joules per gram per degree C, or if you like, 1 calorie per gram per degree C. And mass is the mass of the water. Notice that the mass, this value for C, and the temperature change are all for the water, okay? They're not for the thing that we're putting into the water or what's happening inside of the water or anything like that. It's the water itself, and that's mc delta T, okay? Now Q reaction is actually equal to delta H, all right? It's equal to delta H for the reaction. Now I'm going to qualify that a little bit in another step. So we're gonna qualify this a little bit, but for now let's just say that QW is mc delta T and QRxN is delta H for the reaction that's happening in the water. Okay. Now let's make another distinction. So Q sub W is the heat that is going to be absorbed or released by the water in the cup. Whereas Q subscript Rxn, Q for the reaction, is going to be the energy used or produced by the reaction. It's the energy that's going to be used or produced by the reaction happening in the water. Now this is important that you see that these are two very, well, I wouldn't say very different, but they're two different things that are happening. The water, we have the water absorbing or releasing heat. We have the reaction using or producing energy. Now here's where the connection comes in, though. It turns out that Q sub W is equal to the negative, and I'm going to write it as -1 times Q for the reaction. And so Q for the reaction is equal to the negative of Q for the water. Now what that means, as we've seen before, if I have a reaction happening in here, and if it's releasing heat, then that same amount of heat is being gained by the water. So whatever the reaction releases or produces, the water gains. And whatever the reaction uses, the water loses. So if we dissolve salt in water, for example, if we dissolve salt in water, the water actually gets colder. And what's happening in that case is you've got a dissolution process, not technically a reaction, but you've got something dissolving in the water, and what happens is Q goes out of the water into that dissolving process. All right, and that's where we get this thing, Q sub W equals negative Q for the reaction. All right, so it's very important that you get those clear. And that on the hamburger worksheet, there were some questions designed to get at your understanding of this. For example, if I put, let's say I put 10 grams of NaCl into this water, and then I was doing my calorimetry calculations and I was trying to find Q for the reaction, I would not plug 10 grams into the mass right there, because that mass is for the mass of the water. And that leads me into the qualification that I spoke about with delta H of reaction. So typically Q for the reaction, let's say Q for the reaction was negative 2,700 joules. All right. Now, we typically wouldn't say that delta H for the reaction is negative 2,700 joules. And I know I'm just probably confusing you at this point, but here's why. Because delta H for the reaction is typically written for an actual balanced chemical equation. So let's say I write it like this: NaCl solid is turning into NaCl aqueous, which means dissolved. Okay, and this is just an equation for the dissolution of salt. Then I would write delta H of reaction. Now in this case, what would delta H of reaction be? Well, I've got to, and I'm going to erase this for now, I've got to figure out what delta H would be if a whole mole of sodium chloride, because this is 1 mole, it's not written here, remember we don't write ones in chemistry. So what would delta H be for a whole mole? Well, here's how you do that. This was for 10 grams in this hypothetical example. So what I do is I write negative 2,700 joules in 10 grams, or from 10 grams, and then it's about 58 grams per mole for NaCl. Okay? And that gives me negative 2,700 divided by 10 times 58. By the way, this isn't the actual value for this. These are just made up numbers. This would be 15,660 joules per mole, and with proper sig figs we're more like 2 or 3 here, so I'll just say, and I'm going to just change this to kilojoules, 15.7 kilojoules per mole. So that's what I would write here, except I'm not going to write per mole here. I'm just going to write negative 15.7 kilojoules. Why won't I write per mole? Because when we write it like this on the side of a reaction, we're saying that this delta H is for this whole thing, however it's written, however many moles are written there. Okay? Now, when do we see kilojoules per mole? That is typically when we see something like this, delta H of formation in kilojoules per mole. It might be the delta H of formation of carbon monoxide gas, which is negative 110.5 kilojoules per mole. We might see it in something called the heat of combustion, and maybe like the heat of combustion of propane, C3H8 gas, which is negative 2,220 kilojoules per mole. So we would see, where we would see per mole is when we're looking at a tabulated value, for example, that's based on a compound. So like the heat of combustion of this is 2,200 kilojoules per mole. The heat of formation of this is negative 110.5 kilojoules per mole. Okay, now we're ready to go back and tackle this first problem. We've got to break this problem down. It's kind of a complicated problem, and the way it's worded is not making it easy for us. So let's look what it says. Use the following chemical equations. Okay, so we've got 3 chemical equations right here, to calculate the standard heat of formation. Now, standard just means that little naught symbol there, that little circle. Looks like a degree sign. That just is the standard conditions. That's what it's telling us. So calculate the standard heat of formation of propene C3H6 gas. Now, I could probably look this up somewhere, but in this case, they're telling me to calculate it. Okay. Now, before I go any further, what I'm going to note is that what does this mean, heat of formation? It means that if I were to write this equation, I've got, this is propene right here, C3H6 gas. If I'm going to write an equation for the formation of this according to the definition of heat of formation, that means that I'm forming propane gas from its elements in their standard states. Now, the standard state of carbon is just carbon solid, and that's actually the great majority of elements. Their standard state is just the element symbol as a solid. There's several exceptions to that. One is hydrogen, which is diatomic in its standard state, and it's a gas. All right, and remember, there's some others too. It's hydrogen, and it's nitrogen, oxygen, fluorine, chlorine, bromine, iodine. Now, these nitrogen, oxygen, fluorine, and chlorine are all gases. Bromine is a liquid in standard state. Iodine is a solid. Okay, and most of the rest of the elements, except for mercury, which is a liquid, are just going to be their element symbol with a solid. So this is what I've got for the formation of propene, and now I just have to balance it. To do that, I'm going to need 3 of these and 3 of these. So what they're asking in this question, when they say calculate the standard heat of formation of propene, is they're asking for the delta H of this reaction that I've just written here, the formation of propene from its elements in their standard states. And it says complete this problem in 2 different ways. One, using Hess's law. Then using the standard heat of reaction method. Let's take this step by step and start by using Hess's law. That means I can use these 3 reactions to come up with this reaction here. So my net result has got to be 3 carbons plus 3 hydrogen molecules. So I've got to use equations 1, 2, and 3 to get this equation, the formation of propene. Alright, and then I'm going to calculate delta H on that using Hess's law. Now, so what I need to do is figure out how do I need to arrange 1, 2, and 3 so that when they add up, they'll give me 4, which is formation of propene. So I look and I see that I need propene. I have propene right here, but I need it on the other side. So I'm going to want to flip this first reaction around, which will give me 3CO2 plus 3H2O yields C3H6 plus 9 halves O2. And then I'm going to change this to a positive 1296.3. Now, I can see, though, that I don't have any carbon dioxide or water in my final equation, my goal. So I need to cancel these 3 CO2s out. So what I'm going to have to do is multiply this times 3. And it turns out I'm going to have to do the same thing for equation 3, because I've got to get 3 H2s on the left. So actually, let's do this one step at a time. So this one I'm going to write 3C plus 3O2 yields 3CO2, and then I'm going to have to multiply this thing by 3, which will give me negative 1180.5 kilojoules. Okay, and on this one here, I'm going to have to multiply by 3 also, because I need to get 3 hydrogens. So I'm going to do 3 times this, and so this is times 3 is 3 times negative 241.8, which is negative 725.4. All right, now would that work? So let's write this 3H2 plus, now what's 3 times 1 half? That's 3 halves O2 yields 3 H2O. All right, now I can see that I'm going to be able to cancel, when I add these all together, I'm going to be able to cancel the 3 H2O. It's going to cancel the 3 CO2. I'm going to be left with 3 H2, 3C on the left, and then 3 O2 plus 3 halves O2. All right, what's that? So that is 6 halves plus 3 halves is 9 halves O2, which will cancel this. And that gives me what I'm looking for. So let's just do our final calculation now. I'm just going to add this, this, and this. So I've got 1296.3 minus 1180.5 minus 725.4 gives me negative 609.6 kilojoules. Okay, so that's the first method. Now in the second method, it says using the standard heat of reaction. Okay, so let's get rid of all this stuff. I'm going to use a totally different approach. Well, it's really not totally different, is it? Because the equation that we're going to use, which is heat of reaction equals the summation of the delta H of formation of the products minus the sum of the delta H of formation of the reactants. That is actually based on Hess's law, so it's not really unrelated. But what we're going to do is we're going to basically set up this equation as if we were going to solve for the final result. But because we know the final result, right, which is right here, what we're going to do is solve this for this one here. I mean, not solve it, but set it up for the first equation and then solve for the unknown heat of formation of C3H6. So what's that going to look like? Well, the heat of reaction is negative 1296.3 kilojoules. Okay, and by the way, this really shouldn't say kilojoules per mole right here, although it says heat of combustion, so I guess it can. Heat of combustion of propene. So I've got negative 1296.3 kilojoules, and that's the heat of this reaction. It's the heat of combustion of propene for 1 mole of propene. Okay. Then it's going to be the delta H formation of the products. So what are the products? I've got 3 CO2 and 3 H2O. Okay, so I need 3 moles of CO2 gas times the heat of formation for that. Well, what's that? They didn't give it to me. Oh, yes, they did. Look at this. Did you notice that this is actually the equation for the formation of CO2 from its elements in their standard states? Of course you did. So this is delta H formation, negative 393.5 kilojoules per mole, so it's going to be times 3 times negative 393.5 kilojoules per mole of CO2. So you'll see that that's going to nicely cancel for us and leave us with just kilojoules. We're going to add this to the other product, which is 3 moles of water, and that's gaseous water. If they would just gave me a table of heat of formation values, I'd have to be very careful that I was using the right value for water. Okay, now that's going to cancel moles of water. And then I'm going to subtract the heat of formation of the reactants. Well, I don't need this because that's 0 kilojoules per mole. That's an element in its standard state. So I'm just going to subtract C3H6, which we don't know, and that is X. It's actually going to be 1 mole, 1 mole C3H6 times X per mole, X kilojoules per mole. X is what we're trying to solve for, which is the heat of formation for propene. So let's, what I'm going to do is just kind of clean this up a little bit. 3 times negative 393.5 is equal to negative 1180.5 kilojoules. And then 3 times negative 241.8 is negative 725.4. So let's put a negative sign right here, minus 725.4 kilojoules. And then I've got minus X. Okay, so that cleans it up nicely for us, and we can solve now for our unknown. It's just going to be negative 1296.3 plus 1180.5 plus 725.4. And what do you know? I get 609.6 kilojoules, which is the same thing that I got using Hess's law. All right, no surprises there, but a lot of stuff packed into here. Really, the primary difficulty with this question is that you need to really understand what this means right here. The heat of formation. Okay, enjoy the rest of that worksheet.